In this podcast, we're going to talk about what solubility is, and then we're going to talk about also types of solutions, as well as all the factors that affect solubility. So solubility is going to describe the amount of solute that can dissolve in a given amount of solvent at a specific temperature. As you probably know from your own life experiences, you can't just add solute indefinitely to a fixed amount of solvent. At some point, it's not going to dissolve, and we will talk more about how temperature affects this a little bit later. So when we talk about solute, we're always describing in grams of solute per milliliters of solvent, and we typically will say per 100 milliliters of solvent, but that becomes more important later. There are three types of solutions. The first is an unsaturated solution. It's exactly what it sounds like. In an unsaturated solution, you still have the opportunity to add more solute, and that solute will still dissolve in solution. So it's not maxed out on the amount of solute that you can have in that solution. Whereas a saturated solution is considered to be a full solution. So you have put into that solvent the maximum number of grams that can dissolve in that particular amount of solvent at that particular temperature. The other one we don't often get to talk about is a supersaturated solution. So this is kind of a unique situation where you can add more solute than you could normally fit into a solution and it will dissolve. So it's more than it can normally hold. Supersaturated solutions tend to be what we call unstable, and your solute can precipitate rapidly. And a good example I like to think of are those reusable hot packs. So when you first have them, they're kind of a bag full of kind of a gelatinous substance, and you have to click a little piece of metal in there. And as soon as you add that agitation to your supersaturated solution, that's just enough to disrupt the supersaturated solution, and it causes all of a sudden at a rapid rate all of that solute to precipitate out of solution. Well, that tends to be exothermic, so it gives off heat also. To reverse the reaction, you heat it and then cool it very slowly so that you can get it back to that gelatinous state. Here we're just seeing an example on this image of solid, this is our solute, solid sodium chloride being dissolved in aqueous water. And this is, I don't know if it's saturated or not. I don't know how much they used. But what you can see is a dissociation of your ions and your ionic compounds. So all the chlorine molecules are being surrounded by the positively charged hydrogens in the water. And then all of your sodium molecules, which are positively charged, are surrounded by your negatively charged oxygens in your water molecules. Solubility is not set in stone. It's not, as we said in the definition, it's a certain amount of solute that's dissolved in a certain amount of solvent at a certain temperature. So the first factor that affects solubility is temperature. For solids and liquids, you're going to get an increase in solubility when you increase temperature. And I like to think of my iced tea versus my cold tea example. Any tea is a lot better with sugar in it. So if I had, say, iced tea and I added one of these beautiful sugar cubes to it, I'm going to have a little bit of a hard time dissolving one or two of those sugar cubes versus if I try to dissolve it in hot tea. Because there's an increase in temperature, I can dissolve more of that solute into that solution. So that's why iced tea disappoints me, because it's cold. It's not able to dissolve all the sugar, and I wind up, when I drink iced tea with a straw, drinking some of those sugar grains. There's a solution to that, and that's sweet tea. Heat the tea up, okay? Dissolve your 3 cups of sugar in it and then let it cool, and it's going to hold more of that solute as a result of that. But keep in mind, as your temperature decreases, you can precipitate out some of your solute. So that's not a given in your hot, sweet tea that you're making, that you're going to be able to keep all of that sugar in it once it cools, because sometimes it does precipitate out. For gases, though, they work backwards. So your solubility in liquids actually decreases for the gas when you increase temperature. What happens is you're starting to boil this off. Your gases are going to actually leave the solution. They're not going to remain in solution. A good example of this is something we call thermal pollution. So you're increasing the kinetic energy. All your molecules are moving a lot more. So what you're doing is you are having a lot of liquids that are escaping into the gas phase. As you increase water temperature, the gases that are dissolved, say in a lake or a pond, are going to leave that lake. So they're going to leave the solution. And once you start to have gases leave, that's going to decrease your dissolved gases, such as dissolved oxygen, which is really important for aquatic life. So we don't want the temperature of lakes and ponds to increase too much, or we're going to lose that oxygen that supports all those living things in that pond, and that is thermal pollution that we see. A good example of this is in Albany, Oregon, with the water gardens out of your book. Besides temperature, pressure also affects solubility. For solids and liquids, this has really little effect on the solubility of those, but for gases, it does play a pretty significant role. So the solubility in liquids will actually increase with increasing pressure, and we call this Henry's law. The higher your pressure, the greater the solubility of the gas in a liquid. So this explains how essentially soda pop works. If you have soda that's bottled at a pressure greater than 1 atmosphere, so right now, roughly speaking, we're at a higher altitude, but right now it's about 1 atmosphere of pressure. If you were to bottle that soda at a higher pressure, you would be able to dissolve more carbonation or more CO2 into that soda, and you can seal it up. Once you pop the tab on your soda, or you unscrew the lid on that soda, you decrease the pressure of the liquid. When you decrease the pressure of the liquid, a lot of that dissolved CO2 is going to start to escape because suddenly your solubility isn't as great. So that solute is going to leave the solution because it can no longer hold that much gaseous solute. Our last 2 factors affecting solubility are particle size and also agitation. So in particle size, if you were to decrease the size of your particle, that's going to increase solubility when you break those apart. So I like to use, again, our tea example when we're talking about sugar. A sugar cube versus just table sugar, where it's a lot smaller particle size. If you were to dissolve both of these in, say, tea at the same temperature, you're going to see this cube is either going to take longer, it's not going to dissolve completely compared to the sugar that's all by itself. That has a smaller particle size, which is going to increase the solubility. It's going to have an easier time dissolving. The last factor that affects solubility is agitation. So when you increase agitation, you're going to increase the solubility. So again, something I can do if I want to really get my sugar to dissolve in my tea is I'm going to stir it a bunch. I'm going to increase that agitation, stir it. That's going to increase my solubility as well. So think about your hot tea or your coffee. If you want that sugar to dissolve, you're not going to let it just sit there at the bottom and wait for it. You're going to stir it, and that will help your solubility.